Hello, in this video we're going to talk about braid invariants. The idea of invariants is more general than just braids, but for our purposes, a braid invariant is going to be some number or property that is preserved as you apply different transformations to a braid. Now, the tricky thing about invariants is an invariant might be shared by multiple distinct braids. So if you know two things share an invariant, you cannot determine if they are distinct or not. However, if two different braids have different values for their some invariant, then you know that the two braids are different. So what braid invariants do is they provide a oftentimes easier way to determine when two braids are different. So the first invariant to talk about is permutations. If you recall from the last video, we can look at how each string starts in Bn and where each string ends. And it turns out that whatever the starting and ending location is, it's always going to be invariant. So if you have two separate braids and they have two separate starting and ending locations, maybe this is the set of permutations for braid beta 1, and for beta 2, maybe beta 2 is a pure braid. Then we know for certain that beta 1 is not going to be equal to beta 2. The second braid invariant to talk about is the exponential sum. Suppose beta is a braid in Bn, and it's written in the form sigma sub I1 to the power of epsilon 1, sigma sub I2 to the power of epsilon 2, and so on, all the way up to until we get to sigma sub I k epsilon k. Here, note that these sigma sub i's are allowed to repeat because our group Bn is not going to be a billion in general. The order matters. But the exponential sum, exp of betas, how we're going to denote this? This is equal to the sum from j equals 1 to k of epsilon sub j. In other words, you're taking epsilon 1 plus epsilon 2 all the way up to epsilon k, hence exponential sum. This is also invariant, so what this means is if beta 1 and beta 2 are in fact the same braid, then it must be the case that the exponential sum of beta 1 is equal to the exponential sum of beta 2. The third invariant I'd like to talk about is crossing number. And the rule for crossing number is if you have a braid, the crossing number CR of di dj is equal to p of di dj minus n of di dj. So what do each one of these things mean? P of di dj is equal to the number of times the string di crosses under the string dj from the left, and n of di dj is equal to the number of times the string dj crosses under di crosses under dj from the right. Now, in general, these numbers CR of di dj is not going to be equal to CR of dj di. However, with pure braids, we have the special case where CR of di dj is equal to CR of dj di, And because pure braids are special, we're going to give this a special name called the linking index, which is going to be denoted LK of DI DJ. We only consider linking index when we're talking about pure braids, but for braids in general, we do not have equality, so we need to be a little bit more careful. So an example of calculating some crossing numbers, maybe we label these strings 1, 2, 3, 4, and this one over here, we have 1, 2, 3. So looking at this first braid, beta 1, we might say that this is the crossing number of 1 and 2. And notice that string 1 never crosses underneath string 2. So this is equal to 0. However, if we go the other way around, if we take CR of 2, 1, notice that string 2 crosses under string 1 from the right. So that gives us 0 minus 1. We have no crosses underneath from the left, only a cross underneath from the right, giving us -1 for that crossing number. Trivially, if we take CR of 4, 1, or 4, 2, and so on, anything with 4, these are always equal to 0, 4 crosses with nothing. And if we do one more example with this particular braid, beta 1, note that the crossing number of 1 and 3 here is going to be 0, because 1 only ever passes over 3. However, the crossing number of 3, 1 is also equal to 0, because string 3 crosses under string 1 from the right first, then later from the left. So this looks like 1 minus 1 is equal to 0. If we look at the second braid over here, beta 2, we can also do this calculation. The crossing number between 1 and 2, notice that string 1 crosses under string 2 from the right. It occurs over here exactly once. So our crossing number is 0 minus 1, or -1. But if we go the other way, crossing number between 2 and 1, we go underneath 1, and then over 1, and then we do not cross 1 again. So this is going to be 1 minus 0. Oops, sorry. It goes under from the right though, so 0 minus 1, it's equal to -1. So there's one final special property to note with this crossing number. It turns out the crossing number, and by extension for pure braids, the linking number is going to be an invariant. And we can say a little bit more about this invariant because we get what's called the commutator subgroup from this invariant. So what is a commutator? What is a commutator subgroup? So in any group, the commutator, if we take elements G and H in a group G, we denote the commutator GH as G inverse H inverse times GH in that order. So we could define the commutator subgroup, which might be denoted as G prime, to be equal to the set containing all commutators, GH, such that G and H are inside of the original group G. What's special about our crossings and our exponential sum is it turns out that the set Hn, which is equal to the set containing all beta in our braid group Bn, such that the exponential sum of beta is equal to 0. This is the same thing as the commutator group of Bn. The commutator group is always going to be normal, so that gives us some interesting properties when the exponential sum is 0. And what we also know is that the sum, such that 1 is less than or equal to I, which is not allowed to equal j, which is less than or equal to n, of the crossing numbers di, dj, is equal to the exponential sum of a particular braid beta. So for any particular braid, these crossing numbers and the exponential sum are closely related, and if you know your exponential sum is 0, you know that the sum of your crossing numbers is going to be 0, and vice versa. That's all for this video. Next video we're going to wrap up by talking about ambient isotopy and how it relates to braids.